NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams. And all these little dots are stars?
All these little dots are galaxies, some of which are bigger than our own.
Breaking news. We may have just found potential evidence of intelligent life beyond Earth.
This is a huge discovery, and we think that it's a huge discovery. And that's the most exciting piece of this telescope, of this remarkable instrument we put in space, is finding things that we didn't expect, that we can't explain, because that means that we have to revise our understanding of the universe.
Well, JWST is so phenomenal that if you spend enough time, you could probably find any galaxy that ever formed in the universe. It's really that powerful.
Terrifying statements by driving astrophysicists Neil deGrasse Tyson and Michio Kaku have carried Pluto back into the spotlight with a staggering revelation. They suggest that this cold world is on a potential collision course with Neptune. Nevertheless, how could this work out, and what could be the results of such a gigantic event? Are we witnessing a captivating astronomical phenomenon, or is there something else to this impending catastrophic effect? Join us as we explore the likely outcomes of a Pluto-Neptune impact. Pluto, a former planet that was downgraded to a dwarf planet primarily due to its unusual orbit, remains a subject of interest and study in the astronomical community. According to recent predictions by leading experts, Pluto's trajectory is perilously close to Neptune's. Tyson and Kaku are raising alarms about a potentially hazardous impact between these two celestial bodies, which could pose a significant risk to Earth. How is such an event even possible? Pluto's orbit around the Sun is unlike any other planet in our solar system. Takes an astonishing 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full revolution. The intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its tilt, measured at 17 degrees to the ecliptic plane. This steep inclination adds layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers sought to understand its unique trajectory. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elongated shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricate nature of orbital mechanics. The three-body problem in space involves understanding how three bodies, such as Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on their starting positions and mutual gravitational pulls. In Pluto's case, this problem highlights how its orbit, Neptune's orbit, and the Sun's gravity interact in a complex manner. Terms like nodal precession, libration, and VZK oscillation are part of this puzzle. According to astrophysicists, resonances play a critical role in stabilizing planetary orbits. In the case of Pluto and Neptune, this means that when Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from colliding. Nodal libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is generally positioned above or below their orbital plane, providing an additional layer of protection against potential collisions. Another key factor in this equation is the VZK oscillation, named after three researchers, von Zeipel, Kozai, and Lidov, who studied the motion of objects in space. This oscillation describes how three celestial bodies, such as Pluto, Neptune, and the Sun, influence each other gravitationally, affecting their movements. In Pluto's case, The VZK oscillation helps explain why its orbit around the Sun is so unusual. Despite Pluto's orbit appearing erratic, this oscillation helps keep it stable over long periods. These factors work together to maintain the stability of Pluto's orbit, ensuring it doesn't collide with Neptune or veer off course. The three-body problem helps us understand how these orbits evolve due to gravitational interactions. Studying this provides insights into Pluto, our solar system, and distant worlds. Numerical simulations in the late 1980s revealed that, despite these stabilizing factors, Pluto's orbit is inherently chaotic. Minor deviations in initial conditions can lead to significant differences over millions of years. However, the unique properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping chaos at bay. Recent virtual simulations have helped us understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit consistent. However, Neptune isn't the only planet at work. Jupiter's gravity also plays a significant role in stabilizing Pluto's orbit, with Saturn contributing as well. These simulations show that Jupiter's gravity alone is strong enough to ensure Pluto remains on a steady path for an extended period, possibly even billions of years. Perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto continues moving safely through space without encountering trouble. These dynamics are essential in maintaining the order and consistency of celestial bodies' movements. Without these mechanisms, our solar system would be a place of much greater chaos and unpredictability. Bodies like Pluto could potentially collide with others or be ejected from their stable orbits, triggering a chain reaction of events affecting other celestial bodies. For Pluto specifically, with discussions about it potentially colliding with Neptune in the future, understanding its orbit is crucial for providing a clearer picture of the solar system's dynamic nature. The case of Pluto illustrates how even the most seemingly chaotic orbital paths are governed by intricate gravitational interactions. The case of Pluto demonstrates the delicate balance that governs celestial mechanics in our solar system. Despite its unusual orbit and proximity to Neptune, it remains stable due to the interplay of gravitational forces and resonances. These forces not only prevent collisions but also ensure that Pluto maintains its path without significant deviations over vast stretches of time. If Pluto and Neptune were ever to collide, the consequences would be catastrophic, not just for the 2 celestial bodies but potentially for the entire solar system. The collision could eject massive debris into space, which could pose a risk to nearby planets, including Earth. However, the likelihood of such an event is extraordinarily low, thanks to the protective mechanisms discussed earlier. The study of Pluto's orbit also sheds light on the broader dynamics of our solar system. It reveals how even seemingly chaotic elements are governed by precise physical laws. Understanding these dynamics helps astronomers predict the behavior of celestial bodies, explore the potential for life on distant planets, and gain insights into the formation and evolution of our solar system. In conclusion, while the notion of a Pluto-Neptune collision may sound dramatic, the intricate gravitational relationships that stabilize their orbits make such an event nearly impossible. Pluto's journey around the Sun continues to intrigue scientists and inspire curiosity, serving as a reminder of the vast, complex, and interconnected nature of the universe. It is a testament to the power of scientific exploration and the endless mysteries that await discovery in the cosmos. Temperamental circles can arrive at a condition of equilibrium through the perplexing communication of gravitational forces and orbital mechanics. It likewise highlights the significance of ceaseless observation and investigation of these phenomena to better comprehend our place in the universe. Exploring the depths of space often leads us to confront the capricious nature of celestial bodies, and Pluto's orbit is an ideal example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions, is strikingly demonstrated in the case of Pluto. This means that even slight changes in the dwarf planet's position or speed can drastically alter its long-term orbit. Using computational simulations has been immensely helpful for scientists in understanding how Pluto moves through space. These simulations use complex mathematics to model how Pluto and other celestial objects, like Neptune, pull on each other. By tweaking small details in the simulations, astronomers can see how even minor changes can lead to significant differences in Pluto's trajectory. Back in the late 1980s, these simulations revealed something intriguing about Pluto's orbit. Even with factors like axial tilt and orbital libration keeping it steady, its orbit can still be highly erratic and unpredictable. If you start with only a small difference in Pluto's initial position or speed, its orbit could end up looking completely different over many years. Yet, even amidst this chaos, Pluto's orbit remains stable over incredibly long timescales, suggesting that its journey around the Sun follows a kind of order despite appearing chaotic at first glance. Looking forward to cosmic events, especially those involving chaotic or unpredictable orbits like Pluto's, poses significant challenges. The inherent unpredictability of these systems means that long-term predictions are often fraught with uncertainty. While mathematical simulations provide great tools for understanding and forecasting the future paths of celestial bodies, they also highlight the limitations of our predictive abilities. These models heavily rely on the accuracy of the initial conditions and the complexity of the interactions they simulate. Any small error or misconception can lead to vastly different outcomes, making precise predictions difficult. Moreover, the chaotic nature of celestial orbits like Pluto's serves as a reminder of the ever-evolving and dynamic universe. While we've made significant progress in understanding space, Pluto's case illustrates how much we still don't know about the cosmos. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It demonstrates how the presence and position of each planet can significantly affect the stability and trajectory of other bodies within the system. So, why are astrophysicists raising concerns about a potential collision between Pluto and Neptune? Despite the complex forces working to prevent such an event, Neil deGrasse Tyson offers an intriguing perspective on the mysteries of our solar system, particularly the fascinating case of Pluto. Known for popularizing astrophysics, Tyson views the renaming of Pluto not as a demotion but as a necessary adaptation to our evolving understanding of the many bodies orbiting our Sun. His approach to celestial mechanics is one of continuous learning and growth. Tyson sees the complexities of orbits like Pluto's as a sign of how much there is still to discover in space. The allure of these questions, according to Tyson, makes astronomy so captivating. He deeply understands how space events and discoveries shape public interest in astronomy. He believes that events like Pluto's renaming or its orbital eccentricities can captivate the public's imagination and spark interest in the universe. Tyson, along with other experts, warns the public about the potential risk of Pluto's erratic path. After studying Pluto for decades, he has raised concerns that the three-body problem could pose a significant risk regarding a collision with Neptune, an event he suggests might be long overdue. He stresses that such an impact could completely alter the balance of the solar system and trigger devastating consequences, even as far as Earth. If Pluto and Neptune were to collide, it would be a dramatic and catastrophic event in our solar system. The collision would release a massive amount of energy, potentially shattering Pluto due to its smaller size and icy composition. Debris from the collision might spread across the solar system, creating hazards for other planets and their moons. For Neptune, such an impact could alter its atmosphere and possibly its orbit, depending on the specifics of the collision. Michio Kaku, a renowned theoretical physicist known for his work in string theory and as a science communicator, brings a unique perspective to this discussion. His views on the future of space exploration and the interplay between celestial mechanics and theoretical physics provide profound insights into the mysteries of space. Kaku sees the study of Pluto and its orbit as a window into the future of space exploration. He believes that understanding the intricate gravitational interactions and orbital mechanics of celestial bodies like Pluto can offer vital insights for future space missions. This knowledge can help in exploring the solar system more effectively, predicting potential hazards, and even planning missions to the outer reaches of our solar system and beyond. Kaku emphasizes that the lessons learned from studying Pluto's orbit can be applied to exploring other celestial bodies, providing a roadmap for how we might approach and understand distant worlds. While discussing the physics of planets, Kaku often highlights how celestial mechanics and theoretical physics are deeply interconnected. He believes that the movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are not isolated phenomena. They are tied to the fundamental principles of physics. Kaku's work in theoretical physics, particularly in string theory, seeks to understand these principles at the most fundamental level. He often suggests that by studying the intricacies of celestial mechanics, like Pluto's orbit, we can gain insights into the underlying laws of the universe. Like Tyson, Kaku has warned about the potential impact, linking it to his theories about the universe. If Pluto and Neptune were to collide, it would be a monumental event in astronomy, offering a unique observational opportunity that could align with string theory. String theory, a theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional strings, attempts to describe the fundamental forces and matter in the universe. A collision of such magnitude in the solar system might generate extreme conditions of energy and gravity, potentially creating scenarios where phenomena predicted by string theory could become observable. For instance, the high-energy impact could provide insights into the behavior of fundamental particles and forces under extreme conditions, key areas of interest in string theory. Furthermore, the gravitational waves generated by such a collision could provide valuable data for testing predictions from string theory related to gravity and spacetime. These waves could carry signatures or anomalies that align with or challenge the predictions of string theory. While the direct impact on Earth would be minimal due to our distance from the outer solar system, the scientific repercussions of such an event could be enormous, contributing to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's orbit is a marvelous example of celestial mechanics at play, demonstrating both stability and chaos within our solar system. The unique qualities of its orbit, influenced by the gravitational forces of neighboring planets, especially Neptune, highlight the unpredictable and dynamic nature of space. The three-body problem isn't the only mystery of the universe. We have yet to solve many others. Potential catastrophes are expected to occur in the future. While the possibility of planetary impacts in space is truly fascinating, it cannot be completely ruled out. The dynamics of planetary orbits can be affected by various factors, including the gravitational interactions described by the three-body problem. In systems with multiple planets, such as the TRAPPIST-1 system, which contains 7 Earth-sized planets, these planets can pull on each other with their gravity, creating a rhythm or pattern in how the planets move, known as orbital resonances.